Welcome to a lesson with Dr. Powell. Let's take a look at how we can show that a short exact sequence that splits on one side um, is actually has a splitting on the other side, and B in particular is isomorphic to the direct sum of A and C. And we're going to do that using universal properties and maps or morphisms between things. Okay, let's kind of get some intuition. First of all, if you have an element in B, what we'd like to think of it as is as an ordered pair. Now, what is an A actually is already given by the splitting. You send this ordered pair down through and bring it back, you should get an element of A. The question is, what is the element of C? Well, naturally, well, let's think about that. Well, what if you took this itself and just subtracted off what you got from A? It's like taking the identity map on or identity morphism on this and then subtracting off what you did to get A, which is essentially this identity minus, here you go through gamma, then alpha. And that's what we're getting here. So that should be the element of C that we desire. Now, you might notice that if we were to run this map against itself twice, we actually get the same map again using the fact that, and here expanding this out and using the fact that gamma of alpha is just the identity over here with that splitting. Okay, and that's kind of nice because that's exactly what happens over here. When we get the thing for A and send it back, we keep on getting the same thing over and over again. That's what we should be getting. So, so that's hopeful. Now, so if we run this map, and let's call this map identity minus alpha of gamma, let's just call it omega, and we take it to the image of omega, so letting omega be this guy right here, we'd like that these two guys to be actually be isomorphic. I mean, that would be nice. And the way we're going to do that is we're going to show that A is the that A is actually equal to the kernel of both of them. I mean, we know A is equal to the kernel of beta. Now, is it equal to the kernel of omega as well? Now, if so, then we'd actually, then, this being the kernel, then we'd actually know that the image of omega here would be the, should be the co-kernel of, it should be the co-kernel of this map. And so basically what we have is we have these two co-kernels. These would both be the co-kernel, and by uniqueness of co-kernels, I mean, these would be the exact same. So that would be very handy. So we're going to show, so basically what we're going to do is we're going to show that A is the kernel of omega. So we're going to use a universal property here. First, let's think about what a kernel is. It's the fiber product, the zero there. So here, let's suppose we have something going like this with an F here. Well, notice what we'd like to do is show that A satisfies the universal property for kernel in this diagram here. Notice that we have a map that goes like this, which is simply gamma of F, which is already given here, F gamma and alpha, right? So gamma of F, it's right here. So we're almost done. We just got to show that's unique. So particular, we know that F is equal to alpha of gamma of F. And then we also, well, what if there was another one like G, right? Okay, what if that was equal to that? All right, so then what we'd get, if we subtract these two, we'd end up getting something like 0 is equal to alpha gamma of F minus G. Using the fact that alpha is a monic, it's a kernel and factorization is unique. So if we have 0 coming through, that was a 0 coming before by that uniqueness. So this is alpha is monic, and this is going to be 0 there. So hence we know that it satisfies the property. So indeed, A is the kernel. It's the kernel of this map. And this map, so in particular, means that this is the co-kernel of that, and that's the co-kernel of that. And so by uniqueness of co-kernel, we get that these are two are the same. So if these two are the same, we're just about done. What we have, we're just about done. In fact, we know that this map right here actually splits, and that was from that idempotency. This idempotency gave the splitting. We bring it forward, and then we do it again, thinking this is in B, and it brings it back to the same place again. So if we just kind of take that splitting and put it down here, we naturally get a splitting over here. So we get a splitting in both places. Okay, so we know it splits both ways. Let's call this map, give it a name like tau, say. Okay, now what about the being isomorphic to a direct sum? Well, that would follow if, let's just think, A and C, and think, okay. So the way that a direct sum is, set up with its universal property, these arrows go into it. What we'd like is an arrow coming down like that, so that we actually get a short exact sequence. And then we get a short exact sequence with commutativity if we get a map coming from between here and here, which we could get by universal property. And then with these being the same, those being the same. And then if an isomorphism here, an isomorphism here by a phi lemma, and get an isomorphism here, we'd be done. So all we really need is just to finish this off is just to make sure we have splitting right here for this, for the universal property of direct sum. But that's not too bad. If we just think about using C itself and considering this as being the zero map, and this is being equal here, there'll be a unique map here that makes this commute. Yes, and there will be going back, and that map actually is a splitting. That's the splitting map that takes you to here, which will give you a short exact sequence. And then, as we discussed before, by like a short phi lemma or something like this, this will be isomorphic to that. So we get a nice isomorphism. So splitting on one side gives you the splitting on the other side. The same argument can be used symmetrically to actually get the, if this has a splitting over here, to get the splitting on the other side. And it works great. So there's just a little discussion, a few notes on short exact sequences and splitting. Thanks for watching.